Hello everybody, welcome to another MCAT ACE video tutorial, and in this tutorial we are going to be examining resonance and formal charge. So this is a general chemistry concept that really bleeds over into a lot of organic chemistry. Resonance can be applied through all chemistry disciplines, but organic chemistry is where most undergraduates first come across the concept of balancing charge over a molecule in different locations. And formal charge is most definitely a general chemistry topic. So we want to take a look at both of these. And I should mention this is it's a standalone lecture, but it is sort of a continuation of Lewis structures because we're going to be talking about Lewis structures in here. We will be going through and developing some Lewis structures of charged compounds, and that's essential in order for us to take a look at resonance and the behavior involved with resonance. So I just wanted to mention that if you haven't checked out the lesson on Lewis structures or you feel like you need a refresher on that, I would suggest you go to that video. If you are comfortable with Lewis structures, then by all means continue forward with this lecture at this point. So let's go over what we will be talking about here in terms of a brief overview. First, we're going to take a very small refresher on Lewis structures. Again, there's an entire lesson dedicated to that. I'll sort of be talking you through it as we set up our first molecule to discuss formal charge and resonance. So we're going to examine a Lewis structure with a charge. So you can expect us to be drawing out some sort of ions. So in previous lectures, we've been talking about carbon dioxide or water. Now we're going to be talking about things like the nitrate ion, the carbonate ion, some of those common ions we could come across. And those will give very good examples of how to calculate formal charge and also how we would go about looking at resonance. Once we have Lewis structures that involve a charge, we will look at calculating the formal charge on the individual atoms in that structure. And then we will look at how we represent, this will be pretty brief, but we'll take a look at how we represent the molecule's formal charge as a whole. So if I have an entire molecule, that molecule has a formal charge associated with it, along with the individual atoms inside the molecule. And you sum all of those up together, you get your total formal charge for the molecule. And then we're going to take a detailed look at resonance and what resonance is. So we are going to cover a couple of topics here. Number one, the fact that resonance offers great stability to molecules and some of the effects it can have. And it basically does this through delocalization of a charge. And we'll talk about what that means in the term delocalization, okay, to disperse. And then we'll talk about the reality of resonance. There are a lot of misconceptions out there among undergraduates in terms of how resonance actually works, especially when we start looking at individual resonance structures. Students have a tendency to think that these exist in reality when that's not the case. It's really a combination of all resonance structures. So we'll take a look at that and discuss that. And then finally, we are going to take a look at the major and minor contributors in resonance. So sometimes you will have equal contributors in your resonance structures in terms of the atoms that are hosting the charge that's found. However, sometimes you'll have one atom that is taking on the bulk of the charge or more of the charge in comparison to another atom. And in that case, you would have what's called a major resonance contributor and a minor resonance contributor. So that's the last thing that we'll discuss to sort of wrap up resonance. And then, as usual, we'll go through some problems and we will also do a summary at the end to make sure everybody is on the same page in terms of all of this content. All right, so to start off, let's go ahead and bring up the whiteboard portion here. And I'm going to work with, as I mentioned just a moment ago, the nitrate ion. So nitrate is NO3 minus. So this is a very common anion that you learn in general chemistry. And the structure of this ion is ideal for explaining both resonance and formal charge. This is one of the ones I always lead off with when I'm trying to explain this topic. I think you'll find that it really shines through as a good example of this sort of stuff. So first of all, we need to create the Lewis structure for the nitrate ion. So let's remember what our rules are here. First, I have nitrogen and oxygen. I need to take, of those two atoms, the least electronegative, and that one would be nitrogen, and place that at the center of my Lewis structure. So nitrogen will be the center. All right, and then what I will do is I will create single bonds to all of the oxygens, but let's think about my valence electron pool here. All right, so my electron pool for the nitrate ion, the nitrogen is going to provide 5 valence electrons, and the oxygens will provide 6 valence electrons. There are 3 of them, so 6 times 3, we're dealing with 18 that are provided here. All right, now if I sum this up, I'm going to look at this and I'm going to say, all right, I have 18, so this comes out to 23 if I add the 5 to that, right? 23 electrons. There's something that should be a red flag to you here, and we didn't really discuss it in the last lecture, but it's coming up now. You should never be coming up with an odd number of electrons unless you have a situation where you have a free radical, and that is a very rare case when you have electrons that are in isolation, they're not paired up. And when you think about this, this is because whenever I'm dealing with a bond has 2 electrons, and whenever I'm dealing with a lone pair, the term pair itself is telling us that there's 2 electrons. So electrons come in bundles of 2 when we're dealing with bonding structures. Again, unless we have a free radical, which is a very rare example. All right, so if I have 23 electrons, that's an odd number of electrons. There's going to be an electron left out here. So what we're forgetting is the fact that this has a negative charge associated with it. And when you have a negative charge, it means there is 1 additional electron present that needs to be accounted for. So this is something different than what we saw before, because before we didn't have to worry about charges, but now if we have negative charges, we need to add electrons to the electron pool, and if we have positive charges, we need to remove electrons from the electron pool. So if you ever come up with an odd number of electrons, chances are that you forgot about a formal charge, and you need to account for that when you are dealing with your electron pool. If you forget, what's going to happen is as you go through and you attempt to do your Lewis structure, you're going to come to a point where it doesn't make sense or you can't properly finish the octet. And you will end up screwing up the Lewis structure if you don't account for the formal charges. All right? So very important lesson here. You need to account for formal charges when you're dealing with Lewis structures in terms of the total valence electrons. All right? And remember, an electron is negatively charged. So if I have a negative charge, I'm going to be adding electrons based on the negative charge. If it's a positive charge, I would be removing electrons because that means that I have more protons than I do electrons at that point. Remember, the charge, the negative means add electrons. A lot of students get confused with that because they think, oh, if you're talking about adding, meaning plus, they're looking at the charge and saying plus means I should add electrons. No, the plus and the minus deal with the charge associated with the molecule, and negative charge comes from additional electrons. All right? So then I draw a single bond to every outer atom per the Lewis structure rules that we went over in the previous video. And when I'm taking a look at this, I need to make sure that I fulfill the octet of all the outer atoms. So here we go. I'm going to start pairing up. And then once I do this, I need to stop because I'm about to put a lot of electrons here and make sure I either haven't gone past the electron pool, or at the very minimum, if I've depleted it, I cannot take any additional electrons for myself. So let's look at this here. Every single oxygen has 8 electrons around it. 6 of those come from lone pairs, and then 2 of those come from 1 bond. So there's a total of 8. We do this 3 times. 8 times 3 is 24. I've now depleted my entire electron pool. So that's it. Now, if we take a look, all the outer atoms are satisfied, but the nitrogen only has 6 of its 8 required valence electrons for a full octet. Because all of these oxygens are equal, we're going to pull from any one of them in order to finish up the Lewis structure by bringing it down here. And then we can show this molecule as N double bond O. Now, because it didn't matter which one I pulled from, it would also be acceptable if you had the oxygen down to the right or down to the left with this same sort of charge here. Or I'm sorry, the same sort of bonding structure that you see at the top. I'm thinking ahead of myself as we're about to talk about formal charge in a minute. All right, so this would be, what I'm about to put in brackets here, this would be the nitrate ion. Okay, so this is nitrate. ATE. If you were dealing with nitrite, you would be talking about less oxygen. It would be NO2. All right, this is the nitrate. So when I take a look at this, I know that the overall charge is negative. So this is how we tend to represent formal charges on the overall molecule. We say, oh, we're going to put the molecule in brackets, and then we're going to toss the charge up here to represent a negative charge overall on the molecule. But we can go in and we can represent the formal charge on all of these different atoms, and then that will give us a look as to why this negative is distributed to the entire molecule. So that's what we're going to take a look at next. So I'm going to keep the nitrate up there, but I'm going to clear this portion of the board over here, all right? Because we want to discuss formal charge. Now, I just want to remind everybody, if you had issues with putting together that Lewis structure or following me as I was going too quickly, okay, you should go back and you should review Lewis structures before you continue, because formal charge and resonance is a little more in-depth conceptually than just basic Lewis structures are. So you want to make sure that you're totally set with that. So what I'm going to do here is I'm going to bring up an equation for calculating formal charge, and then I'll walk you through it for each of the atoms so we have an idea as to how to utilize this for formal charge. So let me put that equation up and then we'll talk about that together. Okay, so what I just put up is how you would calculate a formal charge for an individual atom. So what this equation states is the number of valence electrons can be subtracted from, when we're looking at this, the number, what you can subtract from the valence electrons is the summation of the number of non-bonded electrons, meaning your lone pairs, plus the number of bonds found for that specific atom. So this may seem a little bit odd at first when you're trying to read it, but as we walk through it, I promise it's going to make sense, and you'll realize this is actually a pretty easy exercise when we're trying to calculate formal charge. So the first thing that we're going to do is we'll look at the formal charge of nitrogen here, all right, because that's the one in the center. And then we have multiple oxygens. So what we're going to do for that is we are going to use color schemes so that we can decide or point to which oxygen we're talking about when we're working with this. All right, so here's nitrogen. I would say, how many valence electrons should a nitrogen normally have? Well, the answer to that is 5, just like when we were calculating our valence electron pool. So the next thing I would do is I would say I'm going to subtract from that 5 the number of non-bonded electrons. In that case, the answer is 0, because all of the electrons that are found in nitrogen's valence shell for this nitrate structure are tied up in bonds. So if you take a look at the nitrate over to the right, okay, the nitrogen should have 8 valence electrons, and we find that in the form of 4 bonds. So what I would say here is there are no unbonded or non-bonded electrons. However, there are 4 bonds, and the double bond, you're going to count every single bond. So the double bond, you count 1, 2, and then both of the single bonds, you would count 3 and 4. All right, so if I look at this, I would say 5 minus 4 is equal to 1 plus. And so 1 plus is the formal charge on the nitrogen when I'm looking at this structure. It would have a 1 plus in terms of its formal charge, right? Now, some students have a tendency to confuse this with oxidation numbers or oxidation states. That is a separate thing when we're looking at oxidation reduction and we're looking at the oxidation state of an atom. The formal charge of an atom is not necessarily tied to the oxidation number or the oxidation state of that atom. All right. Now, it turns out that many times things that have positive formal charges are also going to have the higher oxidation numbers, but don't confuse the two and think that the oxidation number or state of the nitrogen here is necessarily 1 plus just because its formal charge is 1 plus. Separate content, separate issues, so sort those out in your head. All right, so like I said, I'm going to bring up a color scheme here. Let's do red for the first oxygen, so we'll put a 1 here. We're going to say this is oxygen 1, all right, and then we'll do blue for oxygen 2 down here, and then let's go ahead, we'll do purple for oxygen 3. And that's the reason I'm doing this is I'm going to label oxygens over here, and I'm going to calculate them 3 different times. So how do I know which oxygen is which? Well, by color coding and numbering, it helps to sort that out a little bit so we know, oh, I understand which one he's talking about, right? So we're going to deal with oxygen 1 here, which is our oxygen in red. Right? Don't think that this number, again, this is just to sort out what we're talking about. This is not O2 or O3 like ozone. These colored numbers are just for representing for ourselves how we are attempting to sort out the formal charges of each oxygen. So these are going to be similar to one another because they're all oxygen. So 6 is the number of valence electrons. Now this oxygen at the top, when I'm looking at it, I would say, all right, I have a total of 4 unbonded electrons, right? Non-bonding electrons. Because that comes from the 2 pairs, 1, 2, that I find up here. Plus, how many bonds does it have? It has 2 bonds, all right? So when I look at this, I would say, all right, my 6 minus 6 is going to come out to 0. So there is no formal charge associated with the oxygen at the top there. Again, if you had a different structure, whatever oxygen has the double bond is the oxygen that does not have the formal charge associated with it. All right, so now let's go ahead and switch over to the blue. And for blue, that was oxygen 2 down the right for our example. So again, 6 is the number of valence electrons minus, and then we take a look here, we would say, all right, now I have 6 of the non-bonding electrons plus, I only have 1 bond in this case. So 6 minus 7, that's going to be minus 1 as the formal charge for the oxygen 2. And then if you take a careful look, you should realize oxygen 3 is in the same exact state, the same setup as oxygen 2. So again, I'm going to say 6 minus 6 plus 1 is equal to minus 1. All right, so those are the formal charges for all the atoms in this molecule. Any other molecule that you would work with, and we will do another one after this, okay, you would run through this type of exercise in order to find the formal charges. Now, a lot of times if you get familiar with this and you go through exercises over and over and over again, you can start picking up which atoms have the formal charges and which don't based on their structure. But as you're starting to learn this, this formula is going to be the best way. It won't steer you wrong in terms of picking out the formal charges for the atoms. All right. Now, again, how do I determine that the formal charge here, right, is overall going to be considered negative, right? So the reason for that is if I take and I sum this, so I'm going to say, all right, for the entire NO3 molecule, I'm looking at 1 plus, right, plus 0 plus, let's put all these in parentheses, plus minus 1 plus minus 1. These are all the formal charges I just summed right here, okay? So this is where the total is going to come from. It's from summing all of these, taking the summation of these. So then I take a look at it. I say, well, 1 plus, okay, and I add 0 to it. It's still 1 plus at that point. And then I add a negative 1 to it. So if I add a negative 1 to a positive 1, that comes out to 0. And then finally, this last negative 1 over here is 0 plus negative 1 is going to be negative 1 overall. So this negative 1 is exactly what I need to put up here because the formal charge on my molecule, the overall molecule, is negative 1. All right. Now, one of the things that starts to get tricky when you have formal charges is that in some molecules, you're going to have a formal charge that resides on a specific atom and it stays there. It doesn't move at all. And then there are other atoms that have the ability to move the formal charge around. And so this is one brief snapshot of a larger picture in terms of what's going on with the formal charge. And this is where we come to the concept of resonance. So if we scroll back up here for a second, okay, and we say, let's take a look at this. We did our refresher on Lewis structures, right? We did the Lewis structure with a charge, that was the nitrate. We calculated formal charge using our equation, and then we did a representing molecule formal charge. So in other words, we took the NO3 and we showed why it has that negative associated with the brackets up there. So now we need to discuss resonance, because what I've shown you here is really only one part of the overall picture in terms of what's going on with this molecule. All right, so let me erase some of the whiteboard, and then we're going to get ready to discuss resonance here in a second. So give me a second to clean this up, and then we'll discuss that. All right, guys. So I cleared up the board, and what I did was I redrew the nitrate ion, and I have the formal charges basically assigned to their individual atoms. So right now we can see the pluses on the nitrogen. We've got the representative negatives on the two oxygens to the left and the right, and that oxygen above did not have a formal charge associated with it. So in a situation like this, all right, the question becomes, why does the oxygen at the top get to reside without a formal charge, while the other two oxygens, in this case, have to take the brunt of that formal charge or have to assume the negative charges, right? So why am I bringing this topic up, or why am I stating this? When you look at atoms, when you look at molecules, they prefer to be in a non-ionic or a non-ion state. That's usually how they prefer to reside if they're involved in a bonding molecule. So the more charge, especially the more formal charge we rack up overall in an entire molecule, the worse the stability for that molecule. All right? So one of the analogies I like to give when I'm teaching is that a charge is like a hyper child. So the more formal charges, the more hyper children you're responsible for or that you have in your proximity, the more disastrous it's going to become. This takes a lot of energy, okay? So these are high energy molecules when they have a lot of formal charges. It takes a lot of energy and requires a little assistance in order to help deal with this sort of formal charge situation. So that's the idea here, all right? Now, how do we obtain that stability? How do we benefit from that? Well, the answer is through resonance. So what we're going to do is we're going to pass the charge along, or again, if you're taking the analogy of a hyper child, we're going to take the hyper children and we're going to pass them back and forth. Okay, so in this analogy right now, the oxygen at the top that has the double bond, that has no charge associated with it, so that oxygen is on break. It's not watching the hyper children right now, right? It's got a break. It's taking some stability time for itself, some sanity. The other two are dealing with this, right? So what's going to happen is one of them is going to pass off the hyper child to the oxygen at the top. It's going to pass off a set of electrons, right, to the oxygen at the top. And then that oxygen is going to take a break and allow itself a little resting period, okay? And then it'll pass off again and we'll take another one. So that's the idea behind resonance, all right? So the concept of resonance, and this can be difficult to wrap your head around at first, it's taking a non-stable situation, aka a lot of electron activity or formal charge that's building up in one area, and it's dispersing it. The proper term that we use is it's delocalizing it. So think about what it means to be localized. If I tell you I'm going to my local supermarket, I'm telling you that I'm going to the supermarket in my area, the one that's directly nearby, right? So if I'm talking about something that's localized, it's not a good idea, not that it doesn't ever happen, but it's not a great idea to localize charges if you don't have to. You would prefer to delocalize or to spread out, right, to get them out of the general area and pass them around over a larger area. That's the goal of resonance. So resonance is a delocalization of charge in order to disperse electron activity and improve the stability of the molecule. That's the concept behind resonance, all right? Now, when we take a look at resonance and this delocalization, we can follow this with aeroflow, similar to when we talk about mechanisms in organic chemistry, and we start looking at how the arrows or the electrons flow using aeroflow. That's what we can do here, all right? So what I'm going to do is I'm going to show you how this could occur. I need to take a set of electrons. It has to be a set because in order for a new bond to form, I require 2 electrons, right? So this concept shouldn't be too foreign at the moment because when we discussed Lewis structures, we did say in order to fulfill an octet or a valence shell for a center atom, we do have the ability to draw from lone pairs that are on the outer atoms. So what's going to happen is one of these oxygens, I'm going to pick the one out on the right at the moment, is going to take on a double bond. So it's going to take a set of these electrons and it's going to create a double bond or a pi bond with the nitrogen. All right. Now the nitrogen can only have 4 bonds at a time because that's 8 valence electrons. Remember that nitrogen is in quantum level 2, valence shell 2, and in valence shell 2 we do not have d orbitals, so we cannot create 5, 6 type of bonding structures when we're dealing with this. So at the same time, this oxygen, which has had its break from formal charge, is going to assume a formal charge by taking its pi bond and moving these pi electrons up towards itself and saying, all right, I've had my time to rest. I'm now going to take these electrons and I'm going to assume the formal charge that my neighbor down to the right originally had to deal with. And so what this sets up, okay, we show a double-sided arrow when we're doing this, like this, because these structures are resonance structures that are equivalent to one another. So we're not really performing a reaction here at all. What we're doing is we're moving around electrons into either pi bonds, because we're forming a new pi bond and letting go of one, or lone pairs. So the new structure that I would have here now has a nitrogen with the oxygen at the top having 6 non-bonding electrons as 3 lone pairs. The oxygen over to the right is now going to be the one that's taking a break from the formal charge. Okay? And the oxygen to the left is still currently dealing with a formal charge. Okay? So again, going back to you're going to keep hearing me reference this example. If you go back to the idea that the charges are hyper children, right, and the oxygens are responsible adults that are, I'm sorry, I messed that up here. Good thing I caught that. This should only have 2 pairs of electrons. Okay, that oxygen over there on the right, I gave too many electrons to. I wasn't paying attention. All right, so back to the analogy. If you look at the oxygens as responsible adults, right, they are taking turns watching the hyper children and giving one another a break. Okay, so this analogy is flawed, and we'll talk about why it's flawed in a second. But as you're first starting to understand resonance, we take baby steps. You want to understand the general concept of this before we open up the floodgates and start talking about how resonance really behaves and all that kind of stuff. All right, so now let's not forget that the nitrogen here is still taking on the positive charge, right? It's the oxygens that are passing this around. Now, if I take another look here, okay, so which one hasn't had a break yet? The oxygen on the left. So we're going to say, all right, the oxygen on the left can have a break. So what it will do is it will take a lone pair and it will distribute that into a pi bond in order to get out of the formal charge situation. But now this oxygen that just had its break is going to need to reassume the formal charge with its structure. So what this does is this creates another resonance structure, okay, which we'll show right up here. Now, something to keep in mind, the more resonance structures a compound can take on, the greater the stability of that compound, all right? So if I can get, let's say that I have a negative charge on a compound, right? If I can find 2 compounds, one that has a negative charge but has 5 resonance structures, one that has a negative charge that only has 2 resonance structures, then the one that has 2 resonance structures will not be as stable as the one that has 5 resonance structures, generally speaking. Okay, because when we're talking about this, the more we can delocalize the charge or the more stable adults we have in this situation, the better the situation is going to become in terms of the stability and the energy involved. All right, so here is the final resonance structure. I had to delete 1 or 2 things there as I was focusing on talking and drawing at the same time. All right, so negative, negative. So now if I take a look here, every single structure, if I look at them, there's been a chance, right? There's the positive. I don't need to circle that. There's been a chance for each oxygen to take a break in terms of having to host a formal charge. And that's the concept behind resonance. So you want to say, okay, formal charges are not ideal on specific atoms. They want to be delocalized. So how do we do that? Atoms take turns passing pi electrons and lone pairs back and forth. And that's very important. Single bonds, okay, so sigma bonds, cannot break when you're dealing with this. So you cannot involve sigma bonds in resonance. And the reason for that is if I start breaking apart sigma bonds, I then am releasing atoms from the structure, or at the very least, I'm going to be rearranging atoms in the structure. If you notice here, I only moved double bonds and I moved lone pairs back and forth off of atoms. I never took an atom and said, this oxygen is completely going to dissociate from the nitrogen and then reattach to another oxygen. All right? So that's a no-no when you're dealing with resonance. You're not allowed to actually restructure. Then you're talking about isomers instead of resonance structures, structural isomers. So for instance, it would not be appropriate for me to say, okay, now I'm going to have a structure that looks like this. The nitrogen will have an oxygen like this, and then I'll have an oxygen double bonded here, and then this oxygen will be off of here. You are not permitted to do anything like this, where you've rearranged the structure. That's absolutely out of the question. Resonance can only move around pi bonds. Okay, this is okay or acceptable for resonance. Pi bonds, it can be double bonds or triple bonds, and lone pairs of electrons. So when we have electron pairs, those are permitted to be moved around. I will mention radicals. If you do get into situations, I know we mentioned them earlier, they're rare cases, but if you do have radicals, radicals do have the ability to undergo resonance stability or stabilization as well, delocalization. All right, so that is a look at resonance. Now, the next thing we're going to talk about is very conceptual in nature, all right? And that is the reality of resonance. So now hopefully you have a grasp on what resonance is, why it occurs, when we use it, how we use it. So the question is, okay, what is the reality of resonance? Is this how resonance truly occurs? And the answer is no, this is not how resonance truly occurs. What I've just shown you is a series of resonance structures. And resonance structures are individual structures that chemists use in order to show or to formulate where the charges are going to be delocalized. So if you imagine, what we're basically saying is, let's say that we're looking at a map, and there's multiple things on this map, each of which is a major landmark, right? If I look at the map and I point to one of the landmarks, in other words, one of the resonance structures, and I say, that's it, that's the only thing in this area, that's how this area looks. There's nothing else to see in this area. It's just what's represented right there at that point on the map. That's incorrect, okay? It's really, if I wanted to get a proper surveying of the entire area, I would need to look at all three of these important pieces, okay? Now, what's important here is to understand that electrons are constantly moving. So even when there's not resonance, electrons are moving between atoms. When they're in shared bonds, they're spending some time with one atom and then some proximity over towards another atom. They're being moved back and forth, all right? So in the case of resonance, these movements are constant between all of the various structures. So when I say, oh, this one's taking a break, this one's taking a break, that was good at first, but the reality of this is none of these oxygens get to take a true formal break from hosting a formal charge. They don't get to stop and let the other two perform formal charge task and then resume it a moment later. That doesn't happen. What happens is that there's going to be an equal delocalization among all of them. So if there are two formal negatives that are going around here, none of the oxygens will ever have one whole negative charge at a time. At the most, they're probably going to have around 2/3 of a negative charge at a time. So what resonance really does is it takes this charge, this formal charge, and it says, here, you're going to take a little bit of the responsibility, you are and you are, but we're going to break it apart all at the same time because the electrons are constantly moving, okay? So that's where the analogy with the hyper child and the parents taking turns starts to fall apart in terms of the true nature of resonance, because if that analogy was true, the hyper child would be split at the same time 3 ways between 3 responsible adults, and you can't do that because a human being is an individualistic piece that you can't split apart 3 ways. Whereas electrons and electron density, when you look at probability and electron waves and things like that, that can happen. So it can be that the electron density in the overall molecule is split apart equally to all three oxygens instead of forcing one oxygen to assume all of it while another one takes a break, and then forcing that oxygen to assume all of it while that first oxygen takes a break, and so on and so forth. So that's the reality of resonance. If I were to put it in a single statement, I would say individual resonance structures do not exist in reality. It's a combination of electron delocalization. Okay, that's a very wordy sentence. There's a lot of words there, but if you think about that, it should make sense in your head based on everything that we've talked about so far. All right. So individual resonance structures do not exist in reality. We use them to show ourselves the various landmarks of where we could potentially delocalize charges. In reality, it is a delocalization, or you could even say it's an average of charge that is delocalized through the molecule. All right, so that is the reality of resonance. The individual structures do not exist. And again, resonance is very important because it offers stability. Now, I'm going to put up another molecule here that we're going to work with for a second. And this molecule is going to help you understand major versus minor contributors, because that's the last thing we want to hit on our list. And then I am going to, the questions this time, I'm going to have a few that are multiple choice, but I am going to have one that it's going to be a prelude to the other questions because I want you to get some practice in with this, all right? So the structure that I would like to put up here is the following, right? So let's say that I have an oxygen, a carbon, and that carbon is triple bonded to a nitrogen here. All right, so I'm going to lead off here and I'm going to just tell you that this is going to be the Lewis structure. And if I look here, there would be an overall negative charge associated with this structure, and the negative charge would be found on the oxygen. So in this structure right here, that's where the negative charge is. All right? Now, the first task that I would like you to do is see if you could draw the other resonance structure and where the formal charge would be located. So I would pause it for a second, see if you could, based on what I've just shown you here, draw the other resonance structure involved here and assign the formal charge. Don't be afraid to calculate the formal charge if you need to. All right? Okay, so hopefully everybody had a chance to try that out. So here's what we're going to do, and I will show you this with some arrow flow. The oxygen would need to move a set of electrons over to the carbon, and the nitrogen would be able to assume electrons from the neighboring bond that it shares with the carbon. This is also a good time to point out that while we're doing resonance, you can only shift or move these electrons one bond or one position over. So in other words, it would never be okay for me to draw an arrow where I say, I'm going to skip over the bond between oxygen and carbon, and I'm going to send this right over to the carbon-nitrogen area. That is incorrect. When we're dealing with resonance, now if you're dealing with a reaction, okay, and you've got other incoming groups, you can attack wherever you'd like to. But when you're dealing with resonance, these electrons have to be within a local proximity to one another in terms of where they're permitted to move. So this would not be an appropriate example of how I move electrons. All right? So all that being said, the alternative structure, the other resonance structure that I would come across here would be this. All right? So I'd have carbon double bonded to the oxygen, carbon double bonded to the nitrogen. Notice each case carbon still has 4 bonds total. I'm not affecting its valence. All right, but now the nitrogen would have 2 pairs of electrons here. Right? So in this case, if you looked, the formal charge would be associated with the nitrogen in this structure, and it would be negative. All right? So those are the 2 resonance structures associated with this ion. Now, if I were to ask you which one would be the major contributor and which would be the minor contributor, would you be able to answer that question? Well, I can tell you it's going to be based on electronegativity. So see if you can figure this out. I'll give you a second. Again, pause the video to think about it for a minute. Okay, so the answer here is that the major contributor would be found at the top, okay, and the minor contributor would be found at the bottom. Now, what does this mean? Well, first of all, it means that between the two resonance forms, there's going to be a heavier emphasis of electron density. Okay, now I'm making up this number, but let's say 80% of the electron density is going to be found near the oxygen, where only about 20% would be found in the nitrogen form. So overall, if I'm looking at electrons moving and distributing themselves in the molecule, the oxygen doesn't have 100% of all that formal charge. It's got about 80% or a lot of it. And then the nitrogen has 20%. These might not be the actual numbers. I'm just coming up with a random example here off the top of my head. All right. Now, what this means, the minor contributor is not going to host as much of the electron density or formal charge density as the major contributor would. The major contributor, by the very term major, is expected to host more of that electron density. Now, why is this the case? If we look at electronegativity, oxygen is a more electronegative atom. Okay, so this is higher in electronegativity, whereas the nitrogen is going to be lower in electronegativity. So this would be lower. Now, again, when I say lower, that's in comparison to the oxygen. Nitrogen is still an electronegative atom overall. But compared to the oxygen, nitrogen is less electronegative. So these are not equal contributors like we saw with the nitrate example. In the nitrate example, oxygen is oxygen is oxygen. They have the same electronegativity. Therefore, they have the same propensity to share or equalize the charge. Not the case here. Now we've got an oxygen, a heavy hitter in terms of electronegativity, and a nitrogen, a moderate hitter in terms of electronegativity. I would expect that the oxygen is going to spend more time or gather more electron density in its vicinity than that of the nitrogen. And this comes into the concept, this last concept we wanted to talk about, that we can have major and minor contributors, and the answer is that's based on electronegativity. All right. Now, an interesting point here, This was a negative formal charge, meaning there was excess electron density. It is also possible to have a positive formal charge. And if I have a positive formal charge, at that point, I am now looking at atoms that have less electronegativity being the major contributors in that case. So you have to think about, am I dealing with excess electronic property, in which case an electronegative atom would be beneficial, or am I dealing with a lack of electrons, in which case one of the donators or one of the non-withdrawing electronegative groups would be more beneficial in that case. All right, so you have to kind of think in terms of major and minor contributors when you're setting something like that up. Okay, everyone, so I wanted to clear the board here just for a second because there is technically a third resonance structure that this compound can take on, and that is the following. You could have the oxygen with a triple bond, and you could have the nitrogen with the single bond. Now, a lot of times I don't utilize this structure very often when I'm talking about resonance. And that's because while this technically can be considered a resonance contributor, it is a very, very poor idea to use this as one of the contributors. And here's why. If you look at the formal charge, the oxygen here is going to have a plus, and the nitrogen here is going to have a 2 minus. All right? So if you looked at the other forms that we had a net charge of minus overall. It was either on the nitrogen or on the oxygen. But here, we still have a net charge of -1, but we are utilizing additional formal charge in order to achieve that state, right? So we've got a 2 minus. That's more intense than just a regular minus as far as formal charge is concerned. And we're now adding a plus. And the general rule here is that having lots and lots of formal charges built up on one individual molecule is a bad idea. Resonance helps to delocalize the charge, but you do not want to start putting out resonance forms that are going to have astronomical levels of charges. And as you continue to creep up in those charges, it makes the molecule less and less stable. So while this is technically a resonance structure for the structure we just looked at, this is not considered a viable major or minor structure. That would be very, very minor, because you are now building up excess formal charge. So this would be one of the worst sets as far as minor contributors. It would not be stable at all in comparison to the other two that we just took a look at. So I wanted to bring that up real quick. All right. So I think that mostly covers major and minor contributors when we're talking about resonance and moving charges around. Keep in mind, it really has to do with electronegativity and which atom is more electronegative, depending on if you have a negative formal charge or if you have a positive, then you're looking for the electropositive atoms as the major contributors, right? So what I'm going to do now is I'm going to clear the board here, and I'm going to bring up an example for you to practice with. So let's go ahead and do that at this point. All right, so we're going to work with the following. I want you to work with the carbonate ion, okay, CO3, 2 minus, that's where the 2 is. CO3, 2 minus, all right? So a couple things that I'd like you to bring up here. I want to see the proper Lewis structure. Okay, and after you have evaluated the proper Lewis structure, I want you to calculate, you don't have to calculate it if you're comfortable with it, but find the formal charge for every atom. Okay, if you're comfortable just looking at it, that's fine. And then once you have the formal charge for every atom, I want you to show all resonance structures. Again, if you use the arrow flow, that's great. If you're comfortable simply just showing the resonance structures, you understand the arrow flow, that's fine. Okay. And then finally, are there any major or minor contributors? So any major versus minor, you need to determine that. All right. So that's your first question. This is going to take up a bit of time while you're working with this. So provide the Lewis structure here, give the formal charge of every atom involved, show me the resonance structures, and then are there any major versus minor contributors? All right. So pause the video, work on this, and then we will walk through this as we come back. Then I'll probably throw up another 3 multiple choice questions. Simply, again, with Lewis structures, it can get very difficult to test. But we could certainly use some theory questions in terms of resonance and formal charge. That would be a math type based question. So I'll come up with a couple multiple choice ones that are a little more MCAT oriented after that. All right, so test yourself with this, and I'll see you guys in just a second. All right, so welcome back. Hopefully you guys were able to pause the video and work on that. So let's get started with this structure here. All right, so the Lewis structure, carbon is less electronegative, and I'm just going to go ahead and I'm going to toss on the oxygens here. All right, the electron pool, this is where some students might have sort of flubbed up at first. You need to remember when you're dealing with your electron pool that we have a charged molecule here. All right, so when I'm working with this, carbon brings 4 electrons. I have the 3 oxygens. Again, if I have 6 per oxygen, that's going to bring 18 electrons. So I'm currently up to 22 electrons. But you cannot forget that there's a 2 minus, so I need to add 2 electrons to this. And then with what I have here, I've got a total of 24 electrons. All right. This is similar to the nitrate, and I tried to keep this first example similar to it so that you had something to reference off of or scaffold off of. All right. So I would combine all of these together. I get 8 per oxygen, 24 total. So I'm in the same situation as the nitrate. So let's go ahead and move one of these down to form the double bond, the pi bond. And so the first answer you should have had was that the proper carbonate structure looked like this. Okay, so that was the first goal. And you certainly could have, in brackets, provided 2 minus out here. All right. Now, as far as formal charge goes, okay, I'm going to bring this up in a different color. We'll use red here. As far as formal charge goes, you should, for the carbon, all right, carbon should have been 4 valence electrons minus, and we have no of the non-bonding. We don't have any non-bonding. Plus, we have 4 bonds. So carbon, in this case, is going to be 0. Remember in the nitrate example, the nitrogen was +1. Not in this case. In this case, the center atom is 0. All All right, so I will number this oxygen 1, 2, and 3 again. I'm not going to go through the whole color scheme here like we did before. Hopefully you can follow along a little easier. So oxygen 1, all right, and again, if you didn't need to do the calculations for this, more power to you. That's great. Okay, so oxygen 1, 6 minus, now I have a total of 4 non-bonding, plus I have 2 bonds due to the pi bond. That's going to be 0 as well. So I should realize if I have these other 2 oxygens, they're each going to have to come out to -1 apiece because the overall charge is -2. So this guy is 6, okay? And then we have 6 and then 1 bond. So that's 7. That's going to be -1. And oxygen 3 would be exactly the same, similar, very similar to the nitrate example here with the oxygens. And there you go. Those are your formal charges that you would have. Right? So I'm going to clear the board here once again. Take any notes for a second if you need to based on what was there. I'm going to clear the board and I'm going to bring up the various resonance structures that we can have for the carbonate. So let's switch our ink color again here. Okay. And when I draw it, I'm going to go back to the first structure that I drew for the carbonate. So I've got this, and I've got this, and this, right? So this was, let's get rid of that there. So I was actually going to start to draw a negative charge, but we're just going to stick with the electrons here for right now. Okay, so that was the first structure that I had. If I wanted to move this, I would say, all right, I'm going to move this up here, right? And then I can move one of these in to form a double bond. So one of the potential resonance structures that I could have here is going to look like this. And then the double bond is now over to the left here. You could have done this in a different order. It's no problem. All right, but you need to make sure that all of these structures were present. The next one would move this back up, and then we would move this one in. Again, more power to you if you didn't have to use the arrows. You should. It's a good thing to be able to use them because as you need to learn how to do mechanisms and things like that, it's beneficial to learn how to push arrows to show electron flow. But if you were able to do it without it and you're comfortable with that, that's great. That's a double bond there, by the way, that I'm drawing. Okay. Looks a little close together. And there you go. All right, those are all of the resonance structures that you would need to show, whether the arrows are there or not. You can see the double bond is alternated between all of them. All right, and are there any major or minor contributors here? The answer is no. There are no major or minor contributors. These are all equal in their contribution, and that's because they are all oxygen. And when they're all oxygen, they all have equal electronegativity. And that's how we base our major versus minor contributors, is the identity of the atom. Is the atom, okay, any different than the other atom that's contributing? So in this case, the answer is no. There would be no major or minor contributors. These would all be equal contributors to one another. All right, so that takes care of that example. I'm going to bring up several of the multiple choice questions, and I'll let you guys get started with that. And then from there, we'll go ahead and we'll have a brief summary afterwards. So give me a second to bring those questions up, and then we'll get started with those. All right, everyone. So I have brought up some additional questions to test you on Lewis structures, but primarily formal charge and resonance in relation to Lewis structures. So number one, carboxylic acids are more acidic than other functional groups because, and I'll tell you what, I am going to show you the general formulation for a carboxylic acid here, although that's technically something you could be considered to, be required to know. So we have some sort of alkyl group R, and then the structure is C double bond O OH. That is your carboxylic acid structure. All right. So the options there, you can read through them and pick them out. It's going to have to do with likely something we talked about, either resonance or formal charge. But carboxylic acids are more acidic than other functional groups because, and look at those choices. All right. Number two, the structure of ozone, I am going to expect that you can draw that, can best be described as, and there are some options there regarding formal charge. specifically formal charge for atoms, and then whether there's a net formal charge on ozone or not. So if there is on ozone, I have excluded it here. I have not shown it in that O3 representation. So there could be a formal charge associated with the net molecule. That's for you to determine. And then number 3, I've given some resonance structures here, all right? Which is the major resonance contributor in phenoxide. So phenoxide is derived from what is known as phenol, and phenol is an acidic type of benzene ring. So you have an OH here. So these, once you have the deprotonated form of phenol, you get phenoxide. The first structure, if you actually remove the proton, you can see is option A there. So the proton's gone, there's a negative charge on the oxygen. And then look at those structures. Which would be the major resonance contributor in phenoxide? I'm telling you that there is a major resonance contributor. You have to determine what it would be here. All right, so those are the questions. Pause the video and go through them, and then we will come back and we will discuss them together. I will sort of scroll through this again, make sure that you're copying, because I know there's a lot of content there. I'm not fitting it all on the screen at one time. So pause the video, copy whatever you need to, work through it, and then we will go through it in just a moment. So I'll see you guys in a minute. Alright, so hopefully everybody had a chance to work through these. So number 1, carboxylic acids are more acidic than other functional groups because, so you kind of have to understand how a carboxylic acid works here as far as its acidity. This is the acidic proton right here, and so if that acidic proton were to leave, becoming H+, or be taken by something, you would end up with a structure that looks like this, where that's a negative charge on that oxygen. All right, so this would have an alternate resonance structure here that would look like this, where the O at the top would have the negative charge, and then this one would be double bonded. So there's most definitely resonance here. All right, so let's look at these structures. I'm sorry, these answers. They have no formal charge, making them stable. Well, that is true. When I look at a carboxylic acid before it's been deprotonated, it does have a formal charge, and that does make them stable, but that would not lead to acidity, because if something's stable, it's not as likely to dissociate, okay? So answer A is out here, and especially once you get to the deprotonated form, which is what really makes it acidic, there is a formal charge there. It's a negative formal charge. So A is not a good option here, all right? B, the acidic proton leaves behind a resonance stabilized charge. Well, that's very true, all right? So let's look at the other answers, but I'm not going to throw out B right now, because when the acidic proton leaves, it does leave a resonance stabilized charge, and we do know that resonance adds to stability. It makes a better situation out of things. So maybe that acidic proton is acidic or is willing to leave because it leaves behind a stable charge, and that's what makes it acidic. They have 2 resonance structures instead of 1 like most acids. Well, this is a bit of a tricky question, or a tricky answer I should say here. Okay, they do have 2 resonance structures. You can see I've identified them here. Here's 1, right? And here's 2. But to state that they have 2 resonance structures instead of 1 like most acids, that is not a good statement, because if I have, for instance, HCl, which is more acidic than a carboxylic acid would be, HCl, when the H plus leaves, I have Cl minus. There's no resonance there at all. There's not even anything more than an atom that contains a formal charge. So stating that all acids have at least one resonance structure would be foolish. That's not correct in terms of our answer there. And on the flip side, if I drew something like sulfuric acid could have more than 2 resonance structures when I'm looking at all the oxygen surrounding that sulfur. So stating that the problem with this is, while there are 2 resonance structures, to state that instead of 1 like most acids, that would be an incorrect statement, because most acids, they're all over the place. They could have 3, 4 resonance structures. They may have no resonance structures, okay? Although acidic protons are going to usually be based on some level of stability. So in the case of the hydrochloric acid, it's the fact that chlorine is a weak base. And so weak bases make good leaving groups. They dissociate from protons very readily. But that doesn't mean that we always have at least one resonance structure. All right, so that answer is out, even though the first half of it looks tempting. They have additional electrons in the electron pool. This doesn't make any sense at all. So if I look at a regular carboxylic acid, what is this referencing? They have additional electrons in the electron pool. Why? Because of a charge? Is that what we're saying? Or is it because you're talking about once you're looking at the conjugate form here that we have an additional electron? Well, that doesn't really lead to anything related to acidity. So this one is definitely out. This doesn't have anything to do with acidity. So B is indeed our best answer. And it turns out that carboxylic acids are acidic because the proton that is able to leaves behind a resonance stabilized charge. In comparison, okay, so let's compare this to something, because we compared it to other acids, but let's look at a carboxylic acid in comparison to something like an alcohol, right? So if I look at methanol, methanol can be acidic under certain conditions. However, if methanol gets deprotonated, it leaves behind O-, and this oxygen does not have any pi bonds or any other structures that it could pass the charge onto in terms of delocalization. So this is a localized formal charge, not as good on the stability scale, and for that reason, we find that methanol has a pKa, that's acidity ranking, of somewhere around 15.7. You could round that up to around 16. Whereas most of the carboxylic acids, they can vary, have a pKa of around 5. So remember, the lower, similar to pH, the lower you go in pKa, the more acidic. So carboxylic acids, pKa level around 5, whereas methanol has a pKa, or other alcohols have pKa somewhere in the range of like 15 to 20. So you're talking about many, many fold increases, because remember, you increase in acidity 10 times every time you jump on a logarithmic scale like pKa. So the correct answer here is the resonance stability is creating the additional acidity that we see there, whereas similar compounds that have OH groups that can be deprotonated but don't have the resonance, all of a sudden they lose a lot of their acidity in terms of the equilibrium values that we find. All right, so that was a detailed answer, but it's important that you understand what's going into this in this question. All right, so let's clear a little bit of that because we're going to need some more room here. All right, now, number 2. The structure of ozone, O3, can best be described as. So the first thing you should do here is jump right into drawing out the ozone structure, and that will lead us to easily picking out the correct answer. Okay, so this is one half, it's testing your understanding of Lewis structures. The other half, it's testing you if you really kind of understand your formal charge. Because it's all oxygen, oxygen needs to be the center atom this time. All right, which means there would be 2 additional oxygens that I would find here and here. And if I'm working with this, I'm going to say, all right, oxygen would normally have 6. So that's times 3, that's 18. There is no charge that I know of right now, so I'm going to go ahead and I'm going to utilize this, all right, because it just says O3 there. So if I work with this, I give the outer atoms all the possible electrons that they can have. So that's 8 total. And I look at what I have here. I now have 16 because I have 8 on one side, 8 on the other. That includes the bonds. And so if I have 16, that leaves 2 electrons left. Well, the rules for Lewis structures state if I have electrons left in the pool and the middle atom is not properly satisfied yet in terms of its valence, which this is not, I'm going to add those remaining electrons to the middle atom. So I then add 2 electrons here, and now my pool is at 0. So do I have a proper setup in terms of the valence structure? Well, for the outer ones, yes. For the inner one, I still only have 6 and I need 8. Both of these are oxygen, so they're equivalent. So one of them will go ahead and donate. It doesn't matter which. Okay. So this ozone would be an example where we would have resonance that could potentially be going on. Okay. So here is the structure of ozone. This is what you should have come up with that I'm circling up here. This right here is the structure of ozone. Right? Now, in terms of formal charge, we're going to need to go through and we're going to need to take a look at the different oxygens that are present here for the formal charge. Right? So if you do that, I'm actually not going to run through the direct calculations here. You can go back and look in the lecture if you're confused on how to do that. All right, but I'm going to talk about it as I'm going through here. So if I look at this, I would say the oxygen on the, let me bring up my pen here. Okay, the oxygen on the left right here would have 6 valence electrons minus, and then if I sum it up, it would have 6 non-bonded plus the 1 bond, that's 7. So 6 minus 7 is minus 1. All right, so I'm talking through this, but I'm not actually writing it out. The oxygen up here, if I take a look at that, this one's going to be interesting, okay? So I have 6 that I would normally subtract from. Then I have 2 that would be non-bonded and 3 that are bonded. So 2 plus 3 is 5. 6 minus 5 is a plus 1 on an oxygen there. So that's plus 1. And then this oxygen, I would say 6 as the valence, and then I have 4 that are non-bonded plus 2 that are involved in bonds here. So 4 plus 2 is 6. 6 minus 6 is 0. I think I did all the math there correct. All right. So I take a look at this. What is this going to come out to? So first of all, are there formal charges? Yes, there's a -1. There's a +1. Would I have a net formal charge here? No, because when I sum this up, it's all going to equal 0. So let's look at which answer would be best here. Okay, the structure of ozone can best be described as having formal charges. Well, that's correct, but having no net formal charge. Bingo. We're already there. First answer. All right, let's just make sure the others make sense to cross out. So having formal charges, that's correct, but having a net formal charge. Nope, there's no net formal charge. The net formal charge there is 0. It's non-existent. Having no formal charges, that's already out because we know there are formal charges. Having no formal charges, that's already out. Okay, and D should have been one that's easy to get rid of because it says it has no formal charges in the molecule, but it has a net formal charge. How on earth would you be able to say, I have absolutely no formal charges in the molecule, they all add up to 0, but now all of a sudden my net molecule has a formal charge? That is defying electronic rules. You wouldn't be able to do that. So D should have been an automatic cross out, even without drawing the structure. You can't have that. All right, the others, certainly plausible. C is certainly an option. You can have no formal charges present in the molecule, and then inherently you're not going to have a net formal charge. There's lots of molecules that would fall into that realm, okay? Because they don't have formal charges at all, so then they can't have a net formal charge. That's just like a proper statement. All right, so number 3, which is the major resonance contributor in the phenoxide? I would argue out of these 3 questions, this would probably be the easiest. It might be a little more difficult if I asked you to draw the resonance structures. But again, keep in mind in MCAT, you might be required to draw something on your own to figure out a problem, but the questions aren't going to be directly asking you to draw the compounds. So you would most likely be given structures like this and then be asked to see if you understand major versus minor contributors. So in this case, hopefully this is pretty obvious. It's going to be A because we have a negative charge. This is an oxygen where the rest of these would all be carbons that are containing the negative charge. So that's not to say that these aren't important, but these guys over here, B, C, and D, would all be minor in their contribution to resonance, whereas when we're dealing with the oxygen, that would be a major contributor. All right, so that runs through some of the questions. Hopefully you're getting a good grasp on formal charge, Lewis structures, resonance, and understanding resonance. So what I'm going to do here is I'm going to bring up basically a summary page, just discuss some of the things and the points we want to go over, and then we'll wrap up the video there so it doesn't go too much longer, okay? So give me a second to bring that up, we'll review it together, and then we'll be set. Okay, everyone, so here is a nice summary that I think is pretty succinct in terms of what we discussed. So a couple of reminders and points you want to take away. First of all, when we are drawing Lewis structures that involve charges, whether they be positive or negative charges, remember to add or subtract electrons from the valence pool. If you're getting in a situation where you have negative charges, you need to add to the valence pool. If you're in a situation where you're talking about a net positive charge, you need to remove electrons from the valence pool. And just a tip there that we discussed was make sure that you don't have an odd number of electrons. It's not to say this is impossible. You can have free radicals sometimes, but overall, we tend, when we're dealing with stable Lewis structures, to be dealing with pairs and bonds. We're not doing a whole lot of free radical sort of behavior. In terms of formal charge, which is the next thing we discussed, formal charge for each atom can be calculated using the following. Fc, for formal charge of the atom, is equal to the valence electrons that atom would normally bring to the table, minus, and then group this together, the non-bonding electrons involved, and that is the total, not just the pairs. So let's say I have 3 non-bonding pairs or 3 lone pairs. That's 6 for that number, because there's a total of 6 non-bonding electrons, plus the number of bonds that you find associated with that individual atom. That'll give you the formal charge for an atom. Now, how do I get the net formal charge? The net formal charge of a molecule is obtained by summing up all of the individual formal charges, and then many times this value is placed outside of a set of brackets that contains one of the potential resonance formed structures that contains that formal charge. Okay. Now, as far as resonance is something that is going to offer stability to molecules that have formal charges, and it does this by delocalizing the charges. It moves electrons throughout the structure constantly in order to spread or move that charge apart and not localize it on one atom, which again, remember, is high energy and low stability. That's not a good combination. All right, a couple points you want to remember with resonance. Number one, individual resonance structures do not exist. It's only averages, or sort of a smearing out and delocalizing of all of those resonance structures. Now, sometimes you can have major and minor contributors. Remember, this is based on electronegativity. So if I have a negative charge, the major contributor should be the most electronegative atom, and then vice versa. If I have a positive charge, it's going to be the more electropositive or donating atom that I'm looking at. All resonance forms can only move, this is very important, can only move pi electrons and any non-bonding. Now I put any non-bonding because, again, technically free radicals can be moved around, but any non-bonding electrons, whether they be radicals or pairs, can be moved. But key here, you can never move sigma bonds when you are dealing with resonance forms. That's going to break apart the molecule or reassemble it in a different structure. And then you're talking about structural isomers, or you can call them constitutional isomers, whatever you prefer. But it is not a resonance form at that point. Resonance forms are supposed to be, other than major and minor contribution, are supposed to be identical to one another. You should not have anything in relation to moving sigma bonds or restructuring the molecule that way, where you're basically reassembling the skeletal atomic structure of the molecule. That's bad for resonance. So that is a good summary of everything we discussed. Hopefully everybody found this lecture useful, and you now come away with a better understanding of resonance and formal charge. And we will see you guys for the next lecture. Remember to keep practicing.